Hello. Today we're going to talk about how do we find, arc length along a surface, or not a surface necessarily, but along a path, right, or a function, right? How do we find how far a given distance has gone? So far, kind of what we've been doing is finding area underneath of a curve, and then we can always take that area and rotate it, and then we can change that into a volume. Today we're going to talk about something a little bit different. Instead of finding, the area underneath something, we're going to say, well, how far, is that? What's the length along a curve, right? What's called our arc length. That's what we're going to go over today. I'm going to show you a little bit on the examples. You can go ahead and look through the notes, but that's what I'm going to go through is our notes here today. And how do we find arc length? So to give you kind of a motivating piece or kind of a simpler example on that, let's pull up our picture of our function here. So here I've just graphed on Desmos this pretty simple function. It's a parabola. I just turned it upside down. I made it a little bit wider so it looks a little bit nicer here with the 1/4, so it's a little bit wider on there. But the idea with arc length is, if I want to know, say from -4 all the way to 4, what is that? So to get a better picture of that, maybe we'll put that part in orange and we'll say, okay, this is just going to go from -4 out to +4, right? This orange part, that's the part that we want to find. We don't necessarily care about the blue part. I want to know how far is it from that spot over to the other spot over here. And so the kind of idea is, right, let's just estimate it, right? I don't know because it's curvature, it's not a perfect circle, we can kind of estimate it. So I'm going to make a very basic estimation here. Maybe I can start with the point -4, 1, right? That's right here. And I can go up to the point, I suppose, 0, 5. And then we'll just mirror a point over here at 4, 1 as well. So there's 3 points there. I suppose we could just connect those points and then add up these 2 lines, and that's close. I mean, the actual value is this orange line out here is a little bit bigger than the red one, but it's close there, so we could use that. And I suppose, we're in calculus, so if we wanted to make this a little more accurate, we could just add in a few more points in here. Maybe instead of just going from -4, I can add in, here at -2, 4, right? I could add a spot in there and then also mirror that over here at 2, 4. Right now it's a little bit closer. And we could do that, again, go a little bit closer still. Maybe make our spot at -3, 2, and at -1, and let's see, where is that one going to be at? -1's probably going to be at 5 -1/4, right? I'm just going to put that in there. Oops, where did we put this? -3. Oh boy, let's see. Let's just make that one 5 -9/4. So I'll just type it in just like the equation there. And so again, we could keep breaking that. We could do that on this side too, but we can kind of see, yeah, it starts to get more and more accurate as we do that, right? As we go through those points. So what we're going to do is come up with our equation on what does that equation look like? How do we use a little bit of calculus to refine that edge? Again, we're just going to keep breaking it into smaller and smaller pieces and add up those smaller and smaller pieces, which, spoiler alert, you guys know if we add up an infinite amount of things, that's technically an integral. And here we're not finding, area underneath, which usually we say integral is an area underneath something. Although very technically, an integral is just adding up lots and lots of little pieces. It's just usually we add up lots and lots of little rectangles and we get area. But here we're going to add up lots and lots of little line segments, and that's going to give us arc length. That's what we're going to do here. And so that's what we're going to do on this one. So what I'm going to do here, I'm going to, take some of this stuff out. So we go back to just our very first picture because I think it's going to be a little bit easier to see how that works in here. So I want to go back to just these two. Okay. So I'm going to take a picture of this here. Let's grab this thing here so we can draw on it a little bit. Okay. So we'll take that guy. We're just going to throw it in here so we have a picture to look at. And I'm just going to take a look at this portion, this kind of back portion here, because again, we've got a line segment here. And in this case, if we're kind of generalizing to any function, we just want to find the length of this line. So I don't really care that this function, we know what it is. I'm just going to call this f of x, I suppose, right? We want to find the length of this. And you guys know, right, to find the distance along something, it's essentially the Pythagorean theorem. Let me put a line in here. So it's basically, you know, we can go this direction with something. Let's make that a little thicker, and maybe we'll put it in, let's make it blue. That seems pretty cool. Because we can go this way, you know, blue, and then also we can go vertically as well. I'm just going to stick this guy right next to it, and then we'll go vertically also, right? Move that in. So you can kind of make that triangle, and then we take this side squared plus this side squared and take the square root. Now, what would we call these different things, though, in here? That's what we want to know. Well, this up and down part, right, that's just the y stuff. That's for our next example, all this stuff in here. But, oops, let's make it a capital. Delta, that means change. So that's just the change in y. We can do that, right? And then I suppose the other way is just the change in x. So we can put that one in there, right? So in here, this vertical stuff is the change in y. This other stuff is the change in x. Well, hopefully that'll update, or otherwise I'll put that one in there. So we have change in y and then change in x. I suppose it got a little mad at me there. Let's try that again. Nope, still, oh, there we go. So in there, this way is the change in x. So if we write the full formula for the length of this segment, right, we could say, well, that's going to be the square root of the, I suppose, the change in x squared plus the change in y squared, right? That's how long that segment is, correct? And we'll just turn this here and say, yep, that's how long that one particular piece is. It has to be that, right? And now we can take this and manipulate this equation just a little bit more, right? Because we're going to change it around a little bit so that we can use integrals, right? We're going to add up all these little pieces. But before we do all that summation, here I want to change this equation. It's going to seem a little weird right away. But what we can do is take we can basically factor out this change of x, right? I can factor that out. Essentially here, we could divide by delta x squared here. We can take this one and do the same thing. Oh, I don't want to just divide the exponent, but divide delta x squared on this one. And then that will factor out. So let's see if this will work. I'm not sure if this will work on this guy. Yep, sure it does. Wonderful. And so that factors out, okay, all of that stuff. So let's put that big equation in here. Right, looks a little confusing, and yeah, it gets a little bit messy. I'm going to make this thing a little bit smaller. Let's move our delta y in here. So in here, we factored out, and you're basically dividing everything by this delta x squared. We're factoring that out of there. And here we can simplify this a little bit. These two will perfectly cancel. It becomes 1. This, I'm going to factor out the squared option in there. And then this is delta x squared, but we have the square root of that. So we can kind of cancel the squared with the square root. So if we go back in here, I'm going to simplify some of this stuff. Like we said on this part, we can cancel that. This whole thing becomes 1. And then here we're just going to factor this out a little bit. We're going to factor out this squared stuff. So in here, I'm going to put a different sort of parenthesis around it and say that's squared. I know it's like, oh, did we really even clean that up that much? It looks still pretty ugly, right? But here's the key piece in here, right? Because then what we're going to do, right, this is still the same formula. This very top one and this one are the same exact formula. But now we can do a little bit of calculus on here, because we can think about this as though we're adding up all of the little pieces in there, and we're letting that, you know, change of x go to infinity. Essentially what we're doing in here is we're doing a limit, and then, well, let's put it under here. We're letting that delta x go to 0, right? That's essentially what we're doing here. We're letting that delta x go to 0, and then we're adding up all of those different pieces there. Oops, didn't like that. Let's do a sum here. There we go. Right, we're just going to sum up all of those little things. And I'm not going to put the ends and all that really technical detail in there. But that's essentially what we're doing on this piece. So let's go here. We'll add a new sheet in there so we can keep the notes going. And that's what we're kind of doing. We're going to let that delta x go to 0. And now we know when we're adding up lots and lots of little pieces, we're letting the pieces get smaller and smaller, that we can define what these things are. This summation, again, turns into an integral. So when we go in here, as we're letting these pieces get smaller and smaller and smaller, this whole limit part, right, this turns into an integral. That's why we make that integral sign with an S, because it just stands for that summation. We'll say we'll go from A to B. And if we look at the rest of this in here, again, our delta x, that's just dx. That's what that turns into. And this, we've seen this before, right? Delta y over delta x, change in y over change in x. That's our slope. Remember, what is slope in calculus? Slope is just the derivative. This is saying just the derivative of the function, because we're making that get smaller and smaller. It's close enough to the derivative. So in here, we're going to change this to f prime of x. Oops, I got a little weird in there. F prime of x. So f prime of x squared kind of shows up in an integral, which is a little bit different, although we are taking squared and the square root of it. So this here, that's the key piece for our arc length. That's how we'd put that. So let's, maybe make this thing in gold or something like that. We'll really outline it, nice and big. That's our key piece for finding arc length. That's the equation that we're going to use. So again, if this is making sense to you and you just want to jump right into the assignment, you can. So right now, I'm just going to use this in an example. How would we do arc length in a particular example? So this is what we're going to do. So we're going to find the arc length of this guy from 1/2 to 2. But actually, before we do that, we could finish our other example here. Well, we'll go back and we'll do that one. I'll show you that one as well. But here we'll jump into this. How do we find the arc length on here? Again, if you want a picture of that, x cubed over 6 plus 1 over 2x, you can always, go just to Desmos, and just type that right in there. That's not a big problem, right? If you're wondering, hey, what does this thing look like? And we really want to see this from 0, or sorry, not 0, but 1/2. 0 goes off to infinity. So if we did that, boy, we'd be adding up stuff forever and ever and ever. So in here, I got to zoom out a little bit because 6 goes up pretty high. All right, 6 goes all the way up here, up to like 35 or something in there. So we could always put that, 35 and -1. We'll put this out to 10, so it's not quite so far. Oops. So there we can see a little bit of that. We're just looking for how big is this kind of weird looking arc here, which would be really tough to do just normally. With calculus, it's not too bad. So that's what we're looking for, is how long this arc length is. So let's take that in case you're wondering how to look at that here. Boom, I'll just copy that in. We'll just paste that in there too. So if you're wondering and you want to go ahead and look at that picture, there's the picture of it as well. So how we'd go through here, I'm just going to run through our sort of example on this. We want to go from 1/2 to 2. So I'm going to start this, and I'm going to get rid of this big thing. So we would say that this is an integral, and we are going from 1/2 is the lowest part, 2 is the highest part. I don't have to worry about any changing. It's not changing from 0 or anything like that, going off to infinity. And then we're going with our square root of 1 plus. Now here's where things get a little bit different. I do have to be careful because it is the derivative of this function squared. Seems a little different. So first I have to do the derivative of this. So here the derivative here is x squared over 3, because I would drop this 3 down, or actually over 2, because 6 divided by 3 is 2. And then we do the derivative of this part. Really, again, we could say, well, that's x to the negative power. We're going to drop the -1 down, reduce the power here. So minus 1 over 2x squared, right? That's kind of the idea there. And then this whole thing ends up being squared. And then we have our dx. And this is essentially what we would be solving. The key piece in here is that we have to have the derivative in here. That's what we need, right? So I have my notes down here. I want to make sure that, don't make anything too major on my mistakes. And so then the rest of it is just a little bit of algebra, some basic, integration techniques on there. So for example, here, we could take this part. Let me just double check my notes on here. Boom. Yep. And so then in here, we could expand this part out a little bit on this one here. So let me take a look at that. Just let me check my notes here real quick, and then we'll get back to that. All right, I had to relook over a couple things. I was like, oh man, where do we go from that point? So back to our example here, just to kind of take a look at this one. Again, we just expand this stuff out and combine what we can, sort of put all this back together again. So in here, when we expand, we put them next to each other, distribute everything out. I'll let you kind of take a look at that stuff on your own. But in here, when we go through and do that, I don't like how this goes. Let me change the options on here so we make this thing a little bit smaller so we can see that. It makes the picture a little bit grainier, but it does make it easier to see while I'm typing in here. So if we expand this stuff out, right, we'd have this thing times itself, which would change this to x to the 4th over 4. We'd have this thing times itself, which would be kind of its mirror image there, right? And then also we would have them times each other as well. So this times itself would be just another value of 1, but then we'd get that as well. So I suppose that would be -2 in that case. Let me double check on there. Oops, actually, it would be negative because it would multiply times itself and then add them together. So we get 1/16 when we do that, and then there'd be 2 of those. So we'd actually have -1 over 8 in that part. Hang on. Okay, found a mistake on here again, just kind of jumping through those. A little bit tougher when you're working on the computer like that. I forgot, yeah, we have to expand this part. Let's move this out of the way. We take these 2 times each other, not the expanded portion. So there we'd have -1/4 and then plus another -1/4, making that -1/2 in here, right? And then I suppose we can clean this up just a little bit. The -1/2 and the 1 being together makes that become +1/2 in that case, right? And so at this point, this is where this example gets a little bit different. We've simplified this stuff out some, and now our integral gets a little bit grainy, but that's all right. So in here, with our example on that one, oops, don't want that. Let's just insert that back in here. It gets a little bit tougher here because there's square root stuff in here. A lot of the square root things that you guys might be working with will turn into those inverse tangents or sines or secants, things like that. You can turn those, and maybe use your trig functions, use that integral sheet from chapter 5 so we can look these up. This one's a little bit different here. To make this a little bit simpler, because there are a lot of fractions in there, 1/4 being the sort of largest denominator or the greatest common denominator. So in essence here, we could factor out a 1/4 out of this entire thing. I don't want that there. Oops. Okay, we can factor a 1/4 out of here. So that removes this 1/4, that removes the 4th from here. And then I suppose dividing 1/2 by a 4th leaves you with 2 in that case also. So this part in here is actually factorable. That's kind of the different thing. You could check that with Wolfram Alpha if you weren't completely sure, but we can actually factor this down. It might be a little bit easier to see it if we rearrange, instead of taking this, I'll put the +2 right here. We can see that, oh, this is something squared, this is something squared, and then this is a piece. In fact, it's very similar to our piece before. Oops, let's move here. It's very similar to this part factored back down, right? Because it sort of led to this extra piece here. We've just sort of factored back out. So it's very similar to this one in that case, just a little bit different. So in here, what this factors into, this whole portion here becomes, oops, let's actually delete that out of there. I'll insert it in so we can see it a little bit. This whole portion here can factor a little bit. Yeah. Let's here. Now we can see it some. So this portion, if we remove that, would be this part, but the square root of it, so sort of x squared, and then we'd also have our minus 1 over x squared in that case. Yeah, so we'd have that part there. That's what that guy can factor into in there. Right? Did I make a small mistake up here? Well, I did make a mistake back there. Go back and fix that. Now I realize where that mistake's at. This should be positive throughout here. So I'm just going to add little bits here. We're going to change that to positive because when you take something times itself, it becomes positive. So I made little bits of mistakes on there. We'll just fix these to be positive. We'll fix this one to be positive. So make sure of that. And that changes that just a little bit, changing those, which then allows us, again, here, this is really positive. We just got to fix that one. I'm going to go back through each one. So then that makes this part positive as well. It makes a little more sense for that to factor. So it's that thing squared in this case here. Let's see if we can get that. Okay. So we've gotten that part in there. So now it's, you know, this one works out very well. Most of the stuff in your homework should work out also. And we can take the square root of the squared part here. And that's kind of the more difficult part. You know, the difficult thing is the factoring portion in that one. I just wanted to show you guys that also. So here, when we take the square root of 1/4, so I'm going to remove this entire piece. The square root of 1/4 is 1/2. And the square root of that function is just, well, the function, oops, plus 1 over x squared. Now we can close our parentheses there, right? Because that's square root of 1/4 being 1/2. The square root of the function itself, you know, square root of something squared is that. And then from here, now you can do the integral itself, because add 1 to it, this would be x cubed over 3. This here is a -2 power, so we're going to have to, you know, make it into a -1 power and divide by -1. And then we just plug in these numbers and, you know, work that out. So at that point, then the integral is not too bad. After there, I'll put the rest of the notes here, but I won't necessarily talk about that. So you can, you know, check over that and make sure. But that's how you do arc length. It is a little bit lengthy of a process on there. There's a good pun for you guys. But again, there's short assignment on there to work through these things. There'll be a quiz on Friday. So, you know, just to kind of practice that stuff. I'm, you know, not quite sure how that's going to look, if it's going to be like last week where you'll have your own form to fill in, or, you know, if it'll be kind of a multiple choice thing. Still kind of testing out how those things go. But if you guys do have any other questions, let me know on that stuff. And otherwise, good luck on arc length.